Right, we're going to start chapter 12 today, which is talking about statistics. So we've got quite a bit to cover in this material. A calculator is very, very helpful. Make sure you have some sort of scientific calculator or graphing calculator for this information. For function is possible, but there are going to be some symbols that we have to use that will help with a scientific calculator. So we're going to be talking about, in the first section today, just the visual displays, the different types of different ways to represent the data. We're also going to look at some other topics such as central tendency, which is different ways to evaluate the data. Dispersion, which means different ways to determine whether the data is valid or maybe it might be skewed and have too many data values to the high value or high or low end. Sorry, one of these days I'll figure that out. And then we're going to talk about measure of positions and normal distributions. So we're going to look at all of this information. Today we're going to be talking about visual, so we're going to just talk about some basic concepts of statistics, frequency distributions, and grouped frequency distributions. We're going to talk about stem and leaf diagrams or stem and leaf plots, bar graphs, circle graphs, and line graphs. So first of all, some just basic definitions. If we're talking about a population of data, what we're talking about is all of the possible data values involved in that situation. So an example would be if I wanted to talk about population, I could talk about all of the high school students in Virginia. Or I could talk about a sample of data and I could go out and just interview a random group of high school students in Virginia. So sometimes it's difficult to establish a population of data because you have to be able to get to all of the individuals in that population. Whereas a sample, as long as you have a reasonable number of items from that population, then you can get a pretty good idea of how things are going to work. So with statistics, there are two types of statistics. There's descriptive statistics and inferential statistics. And statistics has to do with things like collecting the data, organizing it, figuring out how you're going to present the data, things like that. Whereas inferential has to do with drawing conclusions about the information that you've got. So descriptive could almost be like the people that do the experiments, and the inferentials are the people that actually evaluate the data that they get. So the data that you collect when you're doing an experiment or when you're doing a survey is called the raw data, and that's the information about what you have gotten, the information that you've gotten, but you haven't had a chance to analyze the data yet. And then there are two types of data that you can get. The most common is quantitative, which is just numbers. So you're figuring out how many people like this or how many people like that. Whereas qualitative data would be more on the lines of like what kinds of things people like. So an example here would be quantitative would be number of people in a family or number of siblings in a family. So you have actually numerical values, 1, 2, 3, 5, 4, things like that. Whereas qualitative are different makes of cars, Toyota, Ford, Nissan, Chevrolet, Honda. So some things are easier to manipulate than others. For example, the number of siblings, you could actually take that information and do some sort of analysis with it. Whereas the different automobile types, you would have to figure out something else to do with that data. So again, quantitative is more common, and that's what we're going to be dealing with some of these things. So what you have here is when you have, for example, with the number of siblings, if you wanted to figure out the frequency of households that had one sibling or two siblings, then we're looking at what we call a frequency distribution. And the relative frequency is basically the percentage of occurrences that happened. So if you had 5 families that had one child in the household, out of 10 families that were interviewed, then you would have 5 out of 10, which is half of your families interviewed. So let me give you a chart to show you an example. So we have 10 students in a math class that were polled about the number of siblings in their class, in their families. And what we have here is that of the 10 students polled, there was a student that had 3 siblings, another one with 2 siblings, another one with 2 siblings. One of them only had 1 sibling, and this is the data that we collected. So if we look at our chart, we see that the numbers that occurred are the numbers 1 sibling, 2 siblings, 3 siblings, or 4 siblings. So any of the possibilities, so if there was a family with 8 siblings, we would have to have the number 8 in our chart. The frequency is how many students in our list had 1 sibling. So if we look back at our list again, we only had 1 student that had 1 sibling. We had 1, 2, 3 students that had 2 siblings. So that's where we got the number 3 in this part of the chart. So there were 4 students that had 3 siblings, and there were 2 students that had 4 siblings. There were a total of, again, 10 students that were interviewed. Oops, excuse me, I put that in the wrong place. There were a total of 10 students that were interviewed. And so when we're talking about the relative frequency, we want to take the frequency divided by the total. So it's 1/10, which is 10%, 3/10, which is 30%, 4/10, which is 40%. So if you do this in a calculator, you come out with 0.10, and then you just multiply that by 100 to get the 10%. So these come out to be nice whole numbers, but that doesn't always happen. So what we can do, once we have this frequency distribution, we can do other pictures with this information. We can do something called a histogram. And a histogram is just a series of rectangles. And if you'll notice what we have here, across the bottom were our choices. We could have 1 sibling, 2 siblings, 3 siblings, or 4 siblings. There was 1 student with 1 sibling. There were 3 students with 2 siblings. There were 4 students with 3 siblings, and there were 2 students with 4 siblings. So you'll notice that on the left-hand side is the frequency, and on the bottom is the number of siblings. So this is a histogram. It's just another way of representing the data that's given to you. Another possibility is what we call a frequency polygon. Also, you could think of this as a line graph. And what we have again here is the number of siblings across the bottom, 1, 2, 3, 4. And you'll notice there's a point with each sibling that represents how many siblings there were, and then you connect that together. So again, these are just different ways. So we have a histogram, we have a frequency distribution table, we have a histogram, we have a frequency polygon, and another way again would just be a line graph, which really looks an awful lot like a frequency polygon. It's just that you don't necessarily have the tails at either end where it seems to go on forever. So they're just different ways, again, to represent this information. So then another way that we could group information is what we call a grouped frequency distribution. And this works well when you have large amounts of data, and it might not necessarily be reasonable for you to plot a different point for every single person in that group. So what you have to do with the frequency distribution is do a little bit of an analysis here and figure out how many sets of data do you want to fit into each category. And then you want to try and make the categories or the classes as equal in size as possible. And you want to make sure that there's no overlapping. And you want to try and have between 5 and 12 classes or groups as you go through this. So I think the best way is just to show you an example. So here we have information. There were 20 students that were asked to estimate the number of hours that they spent studying in the past week. So if I took this information and I plotted it, like did a frequency distribution or relative frequency, I could get a lot of information. And so I take all this information and I figure out that there are, if I were to try and do it separately, that there was 1 student that spent 15 hours. But then the next thing I would want to put in my chart would be 16 hours, but there's nobody with 16 and nobody with 17 and nobody with 18. So if I tried to have just a frequency chart that had all of the frequencies possible listed between 15 and 58, it would be a really, really big chart, and it wouldn't quite tell me as much information as I would like to know. So what we do is we decide, okay, I'm going to group together some of the students. So I determined that the range of students was from 15 to 58. So the smallest number of hours listed was 15, the largest number was 58. So then what I tried to do is just split this 58, which was actually, there were 43 people in this category, because again, if you take, oops, let me get my pen, 15 minus 58, you get 43. So the range of values is 43. So if I try and split that between 5, 6, 7 different things, I end up, in this case, I split it among 6 things. So each group is about 9, and I added a little bit of a buffer around it. So you'll notice that my chart starts at 10 and goes to 59, although my data starts at 15. So I gave myself a little bit of leeway on either side, just so that it makes the numbers come out a little bit nicer, and I still get a pretty good idea of the distribution. So we want to know what students were in this 10 to 19 range, and there was only one student in that range. How many students were in the 20 to 29 range? Okay, and so what we're talking about here is when we look at this set of data, 20 to 29 range would be this student, this student, this student, this one, this one. So we have 5 students that are in that 20 to 29 hours range. So that's where the number 5 came from. And then again, there were 20 students interviewed in the survey. There were 20 students interviewed. So this 5% is 1 divided by 20. This one is 5 divided by 20. And that's where the 25% and the 15% came from. So again, instead of having a chart, and what would have happened before is on this side of the chart, I would have ended up with numbers from 15 to 58, and it would have been very spread out, and it really wouldn't have given me a very accurate representation of what I was finding. So when you're dealing with large sets of data, you tend to want to group these and do a grouped frequency distribution. So again, we can take this information and we can plot it in a histogram. And you'll notice across the bottom, we took the different classes and we listed the different classes. So we said 10 to 19, 20 to 29, 30 to 39. And then we, again, used the same frequency just like we did before, and we were able to graph our histogram. Now, in some cases, what you will see across the bottom is not the numbers 10, 19, 20, 29, but what you might possibly see down here, instead of 10 and 19, you might see something that they call the average of those two numbers, which would be 14.5. So there's an example in your book, and it's figure 4 in your book under this section, that shows an example like this, where you have, instead of these numbers across the bottom, you have the average of those two numbers. So this would be 24.5. So just keep that in mind when you're looking at those examples, that sometimes they don't always list the width of the classes down there. So some of the terms that you might see when you're talking about this is the lower class limit is the smaller number. So remember, our classes were 10 to 19, 20 to 29. So our lower class limits are the 10 and the 20. The upper class limits are the 19 and the 29. And the width for each of these distributions is 10. So the width is the difference between those two, the upper and lower, how many items there are in that distribution. Okay, so then another option that you'll see, and probably seen this at some point in time, is a stem and leaf plot or stem and leaf diagram. And what they refer to this is the stem is the tens place of the number that you're looking at, and the leaves are the ones places. And so what we do is we take our stems and we list down the left. So it ends up looking sort of like a histogram. So you'll notice here, for example, the number 15 is our first number, and that's the number 15. So 15 is 15. 58 is down here with the 5 and the 8. 37 is 3 and 7. 42 is 4 and 2. So what you'll notice is what they did is they looked at the first digits of all the numbers, and they noticed that the numbers, again, the range of the numbers was 15 to 58. So that means we needed the numbers 1, 2, 3, 4, and 5 for our stems. And then basically you take each of the numbers in the list and you break it up. So you take the 15 and put it here, you put the 8 here, you took the 7 here, you took the 42 and put it here, and then ideally what you should do in the end is take the leaves and put them in numerical order. And that helps you to do some more analysis on this that we're going to look at some more. So this is what we call a stem and a leaf plot, or a stem and a leaf display is the term they're using. Okay, so I hope this is helping. And then we have something called bar graphs, and a bar graph looks an awful lot like a histogram, except the biggest difference is that the bars are not touching each other. So when you draw a bar graph, you tend to do the same amount of information that you do for a histogram, but when you draw the bars, you don't let the bars touch each other. It still gives you the same appearance as a histogram. You still get the same effect of being able to see how many things are occurring and see that curve or symmetry, but they just don't touch each other. And then we have a circle graph or a pie graph. So when you're coming up with a circle graph, you have to take the frequency distributions and the relative frequencies and figure out what percentage of the circle that you have. So down here we have something very important. When you have a circle has 360 degrees all the way around. So if the relative frequency is 20%, if we go back to one of the charts and say the relative frequency is 20%, then I know that the central angle of my pie has to be 72. So here's my center of my circle. So if you think about 90, and I'm just estimating this right now, 90 would look like this. So a 90-degree arc would look like this. So 72 is going to be, oops, I did a little bit too small there. All right, let's go back again. Okay, so there's my wonderful circle. So again, 90 would be something on this line. There's a 90-degree central angle. So 72 would be something close to this. So we would be looking at this part of the pie as 72%. So what you have to do is take the relative frequencies that are given to you and multiply it by 360 degrees to figure out what angle or how much of the circle is taken up by that information. So this is an example of a pie graph. So when we're looking at this pie graph, clothing is 10% of the expenses. So 360 times 10% is 36. It's a 36-degree angle. So this angle right here is 36 degrees. So you want your pie graphs to be accurate. If you look at this one, 360 times 25% would end up being 90. So if you look at this angle right here, this is a 90-degree angle in this corner here. So again, it doesn't have to be perfect when you're drawing these, but you do have to have a really good idea of how much it's supposed to look like, or else your pie graph is not to scale and you can't use the data accurately. Okay, so then we have line graphs, which if you do any evaluating of the stock market or anything, you'll see line graphs. And a line graph just simply shows you the progression over a certain period of time for data, and it shows you where it peaks and gets higher or where it drops down and gets lower. So here we have, for example, the price of a stock. So we have January, February, March, April, May across the bottom. And then we have the price of the dollars, which is about 350 in January. It was about 550 in February. It was about $7 in March. It was about $6 in April. In May, it was about 450, and in June, it peaked up to $8. So what you are able to do is look at this and see where are the good periods of time for this stock and where were the bad periods. Maybe in January, that's when they first opened up the stock to make it available. And then all of a sudden people began to realize how wonderful it was, and they bought a lot of stock in June. You'll see this a lot of times when there are bad times in the stock market, where you'll see the line graph will drop down significantly, or when there are good times in the stock market where you'll see it peak up. So these are just different examples of some of the different ways of representing data. I hope this helps. Make sure, again, you keep in touch with me if you're having any problems, and have a good week.